This is lesson 1 in the quantitative chemistry for GCSE set of videos. One of the key ideas I want to get across to you is that mass stays the same. One of the things you hear me talk about is I'm a chemist, I'm not a magician. I can make things change colour, I can make things fizz up, I can do all that whizzy stuff, but I can't make things appear and disappear. Okay, so ultimately, a key idea I want you to take away from this lesson is that when a chemical reaction happens, there is the same amount of stuff afterwards as there was before. And one way of thinking about this is this concept cartoon. So obviously in the autumn, dead leaves fall off trees, every day they eliminate waste. Right, and so what happens to the mass of the earth? Right, so in the same way, you can think of the earth as an enormous, great big biosphere, and there's lots of chemical reactions going on there. So when leaves fall off the trees, they're obviously still there. When they rot away, the atoms that go to make up those leaves, they kind of get recycled. They get broken down by hydrotitivores and all that sort of stuff you learn about in biology, but then they get reincorporated into new stuff. So stuff doesn't disappear. That's the main idea I want you to get here. So ultimately, as we know, the mass of the earth should stay about the same. So the key things you're able to do after this lesson is to state what I've just told you. So no atoms are lost or made during chemical reactions, and mass is conserved. We'll explain a little bit more about what that means in a minute. You should be able to calculate the amount of product made from reactant masses. Apologies for the little sort of red thing over here. And write word and balance symbol equations. Right, this is a higher level objective. You may have started to do some of this, but it's obviously a big skill, so we're going to practice it again here. Keywords today are reactant and product. I'm hoping you're familiar with those from Key Stage 3. Mass conservation is the new idea. Word equations, symbol equations, balanced equations, also we've heard in Key Stage 3, but we're going to work on those a little bit more. So the way I like to think about mass conservation is by using Lego. So I'm going to use the medium of Lego bricks here to explain what's going on when a reaction happens. And I'm now embedding a video inside a video, which is very meta. So I'll play this. I'm going to demonstrate mass conservation with a little bit of Lego. So we've looked at something called calcium carbonate in the past, which is limestone. Okay. And calcium carbonate, what you've learned about this formula is that this Ca means there is one calcium in it. I'm going to make that the white brick. There is, imagine there's a 1 next to the C, which means there is one black brick. And there are 3 red bricks. Okay, so this is calcium carbonate. Okay. There's our calcium carbonate. Obviously it looks nothing like the real compound, but we're just going to imagine it in Lego. Okay. Now when you heat calcium carbonate, it decomposes, which means it breaks down. We did see some stuff on thermal decomposition in Key Stage 3. So thermal meaning with heat, and decomposing meaning breaking down. So when it breaks down, it makes 2 things. It makes calcium oxide and carbon dioxide. Now, this is a balanced symbol equation that we'll be talking about in a little bit more detail later on. So what's happening essentially is that this calcium carbonate is breaking apart and rearranging to give me calcium oxide, 1 white brick, 1 red brick, and carbon dioxide, 1 black brick and 2 red bricks. You've noticed that I haven't changed the total number of bricks. I've got the same number of bricks at the beginning as I have at the end. I've just rearranged them, and that's all that conservation of mass is. So in the practical session, you got to mix 2 solutions with each other. We didn't do the one that's in the picture up here because we're not allowed to anymore, because we're not allowed to do lead things. So we had barium chloride and sodium sulfate. So you had those sitting in 2 beakers or 2 measuring cylinders, and you found the mass of each individual one, and then you measured the mass of the final product. So you should have observed that the final mass of the final product is equal to the mass of all of the stuff that went before. So you should have observed a white precipitate happening when you add the sodium sulfate to the barium chloride. And this is what shows you that a chemical reaction has taken place, because you've got 2 clear colourless solutions, and they're making a white precipitate. Now, reactant mass with product mass, so if you add together the masses of the sodium sulfate and the barium chloride, it is the same as the mass at the end, okay? So, and giving evidence to support your answers, that's numerical data. How could you improve the accuracy? Right, there's all sorts of different things you could do there. So accuracy, well, precision is by using a better balance, okay? So that's not the right answer. Accuracy would be to repeat, okay? So you need to repeat experiments to improve the accuracy. When the sodium sulfate, when sodium sulfate was added to the barium chloride, a solid formed, we call that a precipitate. Let me write that down for you so that you have that spelling there, because some people find that difficult. Precipitate. And write a word equation for each reaction observed, okay? So it is sodium sulfate plus barium chloride right, you're going to swap round the metals. So you're going to swap round the sodium and the barium, okay? So you're going to make barium sulfate plus sodium chloride. Right, and for those of you who are on the ball, you know what sodium chloride is. That's table salt. So that can't be our white precipitate. So the thing that's our white precipitate is actually barium sulfate. And if you've ever had a barium meal to investigate your digestive system, that's what's in it. So here's an example of how it might work in exam paper. So this is another precipitation reaction. So in this one, you've got silver nitrate and sodium chloride, which are soluble, are producing silver chloride, which is insoluble, and sodium nitrate, and you've been given a balanced symbol equation below. Now, if you have 1.7 grams of silver nitrate and 5 grams of sodium chloride, it's very simple. Total product, 1.7 plus 0.585. 2.285 grams, okay? Because due to the law of mass conservation, you must have the same amount at the end as you started off with. Something to stretch and extend you is what is the equation, right? So we decided that we were adding, we'll go through our example here, which was the one we looked at in the experiment. So we added sodium sulfate, which is Na2SO4, plus barium chloride, BaCl2. Sorry, those subscripts haven't come out very well here. You must put those as little numbers at the end. Makes barium sulfate plus sodium chloride. Right, so we're going to practice this a lot over the next few months, so we'll not panic too much about it right now. But you've got one SO4 on one side and one SO4 on the other side, so I'm happy with that. That looks balanced. Okay, so we'll give that a little tick. Right, we've got one barium on each side. That looks balanced. Give that a tick. And we've got 2 sodiums and 2 chlorines. And on this side we've got only 1 sodium and 1 chlorine. So the way to balance this is to put a big 2 in front there, and that is your balanced equation. You can have a go at the other equation. It's adding lead nitrate to potassium iodide to give you lead iodide and potassium nitrate. So the last few questions just going through what is happening here. So in this first one, is the mass going to be less, the same, or more afterwards? Right, you've got water and salt. Salt is dissolving in water. The salt's not going anywhere. You can't see the salt anymore. It's in the water, but you know it's still there because you can taste it still there. Okay, so the mass before is going to be the mass afterwards because of mass conservation. Similarly, that is another physical change, ice into water. So the ice is left to melt. The water hasn't gone anywhere. There might be a little bit of evaporation if you're going to be really niggly about it. So you might lose some of the water, but ultimately the mass that's in the ice is going to end up being the same mass of water that's present. Now these ones are the ones to watch, and there'll be another lesson on this coming up soon. In this reaction, a gas is formed, okay? So this reaction here is magnesium plus acid, HCl, going to magnesium chloride plus hydrogen gas. Okay, so and that is AQ, that's AQ, that's a solid. Right, so we're going to have two of these. I'm just going to balance this quickly. Don't worry if you don't follow this too much. There'll be a whole set of videos on balancing equations. But the reaction here is magnesium plus hydrochloric acid giving magnesium chloride and hydrogen. Now the key point here about this is that the hydrogen is a gas and it can escape. Okay, so these bubbles produced during the reaction are the hydrogen gas. When you measure at the end, notice here you've got an open flask. So that gas has escaped. So you would expect the mass to decrease.